Good afternoon, class. Let's begin, please. So we're going to continue today our march through the electromagnetic spectrum. We started with radio waves, and we've kind of gotten stuck in the visible, and I'm fine with that. Like I said last class, for a couple reasons. I can't shoot gamma rays in class, so we'll kind of basically skip that. Sorry. But the other reason is, I mean, we are visual creatures. We spend most of our day walking around looking at stuff. And so I think some of the more interesting things to talk about have to do with visible light, our perception of visible light, our perception of color. And as we've been talking about, I think our perception of light is a big thing to study and to think about. Because, first of all, there's the physical phenomena of photons of different wavelengths, and we call those colors. But really, just about everything we think about when we think about light and color is going on in our brain and isn't going on in reality. So when I see a rainbow, that's my brain interpreting something. When I see a picture on that screen right now, my brain is interpreting that. And so right now I see the whole visible spectrum, everything from red, orange, yellow, green, blue, violet, indigo, all those are on the screen right now, but they're not. As I've said, that projector in the back only makes 3 colors. So if you're seeing yellow right now, that's your brain making up yellow. If you're seeing purple right now, that's your brain making up purple. So a lot of what we're going to talk about has to do with humans' perception of color and light, things like that. A couple of the phenomena we started talking about last class, I realized we need to maybe clarify some terminology. So I started writing down some terminology that I think is worth going over, talking about. So for example, for instance, I think a lot of people, one of my goals in this class is to clarify or to clear up common misconceptions. I think a lot of people sometimes get confused with the difference between centrifugal and centripetal. But we've cleared that up, right? For the rest of our lives, we will understand the difference between centripetal and centrifugal. Good. Here's another thing that people sometimes get mixed up. There's iridescence and phosphorescence and luminescence and bioluminescence and what I forget. Yeah, they're up there. I'd like to talk today a little bit about what all those mean. They mean something specific in the world of physics. Also, reflection and refraction and absorption, all those light type terms sometimes get confused. And last class we talked a little bit about refraction, and I want to get into that a little bit today and talk about the difference between refraction and reflection. And I still get confused about the difference between all those white things like sour cream and stuff. So that's just another example as I was going in my head. There's more. I still don't know the pudding, aioli, I don't know. So someday I'll learn. I'll take a cooking class on that. So let's start talking about refraction. And here's my example of refraction. Hopefully you can see in that picture, that's a blue car driving down the road, driving down a nice asphalt path. And what I'd like you to imagine is that that car is in neutral and just cruising along, just cruising at a constant speed in neutral. And then they come to a boundary where they go from nice smooth asphalt to sand. That's what's on the right there. I think you can imagine what's going to happen to the speed of that car when it gets to sand. It's going to slow down, right? So it's the guy that doesn't have his foot on the gas. He's just in neutral. He's cruising along. And he gets to sand. He's going to slow down. Very similar thing happens when light goes from one medium to another. Now, one thing I should make very clear, light always goes the speed of light. Light always goes 300 million meters per second. That's a constant of the universe. Our whole understanding of the universe relies on that being constant. So that is a constant. If you ever meet someone from another universe, you can rattle off some of the constants that make our universe unique, and the speed of light is one of them. And so the speed of light is fixed. Now that is the speed of light. There's usually a phrase that's omitted there. It's the speed of light in a vacuum. Speed of light in a vacuum. And so when light is zipping through the emptiness of space, like from the sun down to Earth, it's going 300 million meters per second. When light is going through all of the empty parts of a glass or some water, it's going 300 million meters per second. You and I are mostly empty space. Glass and water, anything else transparent is mostly empty space. Vastly mostly empty space, like 99.999% empty space. But light being an electromagnetic wave and stuff being made up of electromagnetically active particles, there's an interaction there. And so name anything. It could be a glass, plastic, water, Cocker Spaniel. It's made of protons, neutrons, and electrons. The protons are positively charged. The electrons are negatively charged. That is charged stuff that will interact with an electromagnetic wave. So when I have light going through a medium, there's going to be an interaction that, from the macro perspective, slows down light. I want to be very clear, you can't slow down light. Light always goes the speed of light, 300 millimeters per second. But as light goes from atom to atom and goes through a process of absorption, reemission, the net propagation of light can look like you slowed it down. In fact, some scientists, I think at MIT, were able to come up with a medium that slowed light down to a crawl. And so the headline was, scientists slow down light. And they did. I mean, in the lab, you can kind of watch it enter this medium, and it goes at a nice human scale pace. But it's just going through a very time-intensive process of absorption, reemission, still going the speed of light. Okay. But when we have light going from one medium to another, like air into water or air into glass, that's happening. Air is mostly, there's not a whole lot of interaction as light goes through air. So the air molecules are pretty spread out. So as light goes through air, it's just pretty much unimpeded. And then it goes into another clear medium like water. There will be a slowing down of light, so to speak, in that light's going to interact with all those water molecules. So light will slow down, just like that car. Now, that's not that interesting if you're just going straight in. Now, if I have my car cruising along constant velocity in neutral, and the car hits the boundary between fast medium and slow medium, you can see that the car's front right tire is going to hit the sand first. I think you can imagine that if that front right tire slows down first and the left front tire is still going fast, the car is going to turn. The car is going to actually steer a little bit. And the car will bend, or the path of the car will bend towards the normal. The normal is that white dotted line that goes across both media. So that white dotted line is the normal. It's normal to the boundary of the two. And the car is going to bend towards that normal. The reason it bends toward the normal is it goes from fast to slow. And when the car hits that boundary, it's going to bend toward the normal. You can imagine a car going from slow to fast. It's going to bend away from the normal. So you can see in that case, the car is in slow sand, and then the left front tire is going to hit the road, and it's going to take off, causing the car to steer away from the normal as it goes from slow to fast. Light is the same way. Now, the one other thing about light, when we're talking about refraction, when this came up last class, is that light's interaction with matter is frequency dependent, and so the higher the frequency, in other words, the shorter the wavelength, the more pronounced that interaction will be. And so here I've got my red car and my purple car. Red is the longest wavelength of visible light. Purple is the shortest wavelength of visible light. And I can see that my purple car, both cars are going to bend toward the normal as they go from asphalt to sand. But my purple car is going to bend a little more. And that brings us to our second term. So what we're talking about is refraction. Refraction is the bending of light across a medium. This brings us to dispersion. We're dispersing light based on its frequency. So this is the act of dispersion, because I'm filtering out or separating out my different wavelengths. I'm dispersing them. So I have this nice beam, like a flashlight beam of nice white light, and it's just all the colors of the rainbow all mixed in there together. Every possible frequency coming off that filament, even some infrared and ultraviolet coming off my flashlight. Then it hits some boundary like that, and it looked like white because they were all traveling together. And all of a sudden I've got the red bending and the orange bending a little more and the yellow bending more than that, and I get that nice dispersion. In other words, a rainbow. So last class when we had the rainbow, that's what's going on. Yeah. Do I mean or frequencies? Or frequency. So the question is, am I when I'm doing dispersion, am I separating by wavelength or frequency? Kind of same thing. Those two have to go together in light, because an equation I threw up like several days ago is good to know. The equation was C equals lambda F. Here's what that means. C constant equals wavelength times frequency. So if wavelength the product of wavelength and frequency is always the same. It's always speed of light. So if one goes up, the other has to go down. And so red light is long wavelength, low frequency. High wavelength, low frequency. Purple light is high frequency, low wavelength. So there's just so what comes out of the prism can be thought of as dispersed by frequency or dispersed by wavelength. Kind of they go together. Yep. Slow to fast bends away from the normal. Yeah. So the question is about which bends more. Higher frequency, low wavelength bends more. You can kind of think of it. Yeah, so I like to think of red light as these long, lumbering waves. I mean, they're long in that they are 700 nanometers, 700 billionths of a meter. They're very small. But I like to think of them as long, and they do that bending less. Whereas the purple is very short wavelength, and it bends more. Oh, yeah, the effect is more pronounced. Whether it's bending away or toward, the effect is more pronounced for purple. So it's going to bend. So if it goes from slow to fast, it's going to bend away. And it's going to bend away more if it's purple. If it's going from fast to slow, it's going to bend toward the normal. And that will also be more if it's purple. Did I? Yes, like purple. Red has the high wavelength, low frequency. Yeah, no, it's okay. Really. Good question. So the question was, what would like a fast medium? The fastest is a vacuum. I don't think you can speed up. Yeah. The fastest, if you wanted to get light from here to there, you would send it through a vacuum. A slow medium would be a transparent, because it would need to be transparent, but very dense solid. And a dense solid with probably some free electrons, but then it wouldn't be transparent. So a dense solid. And when scientists want to slow down a lot, they come up with these clever combinations of chemicals. But it's called the index of refraction, and you can look it up. And so like water is like 1.4. So air, I think vacuum is 1, and water is like 1.4. Diamond is 1.8 or something. And you can get to 2 or 4 in normal materials, and then crazy scientists get even higher than that. Yeah. Yeah. To you. Yeah, so that's a good example. If you've ever seen a pencil in water, or the place I've seen is at the pool when you watch the guy with the long pole cleaning the bottom of the pool, it always looks really bent, and that's what you're seeing. You're seeing air, you're seeing water, you're seeing light go through the water, bounce off the pole or the pencil or whatever you're looking at, and come back to your eyeball. And actually, that brings us to our next thing, which, in a second, which is, I think is good. So here's something that worth noting. When you get hit with a photon, your brain is going to make inferences about where that photon came from. So when you get hit with a photon going like this, your brain assumes it traveled in a straight line. Your brain is really bad about that. If you get hit with a photon going this way, your brain is just going to trace a straight line back from where it came from and assume it traveled in a straight line. And a lot of times it doesn't. So my brain is going to assume that pencil is bent or that pool cleaner is bent. That's the picture my brain's going to paint. But really, it's not bent. It's just coming at me from, it's been bent at the surface of the water. So the light bends like that, and my brain just assumes it came in a straight line. Yep. Yes, high frequency, low wavelength. High frequency will bend more. Short. Yes. So here on this chart, you can see red has these long waves, and the waves get shorter and shorter and shorter over towards gamma. So I go from a kilometer with AM radio waves down to a quadrillionth of a meter over in gamma rays. So those waves are getting shorter. So the length of them is getting smaller, but their frequency is going up. And so you can see the frequency down here. So the frequency of AM radio is in the kilohertz region. The frequency of visible light is in the terahertz region. Our microwave that we had up here was in the gigahertz. These are all just nice SI prefixes to know. Giga, mega, tera, peta, blah, blah, blah. And then X-rays are in the whatever 18th is, like exahertz or something. So crazy high frequency, low wavelength. Crazy small, crazy fast. Question in the back. Yes, exactly. So let's look at a picture of, this came up a little bit last class. I have another, purple's on the top. Purple's on the bottom. Let's see. Light is, that one's got purple on the top. Purple's always on the bottom, right? Yeah, purple's always on the bottom. Okay, so this picture's good. So here's what's going on, is I've got the sunlight coming from, this picture I just Googled a second ago. Oh, by the way, if you want to find a good explanation of where rainbows, don't Google where do rainbows come from. Then you just get a bunch of pictures of unicorns. You have to Google how are rainbows made. Or one of them just got unicorns. The other one got you physics. But anyway, so I just found this one. This was the picture I had in my head that I was trying to communicate to you guys last class. And that is the sun is coming over my head, and if it hits a raindrop, it might come back to me. It might come back to me due to total internal reflection. That's a mouthful. Total internal reflection inside the raindrop. But if it comes back to me, it'll come back to me dispersed because the purple got bent more and the red got bent less. And yes, that is the answer to why the red's on top. Okay, lots of good questions. And that's also a nice picture of, that's another reason I pulled this up, is a rainbow is just, if you remember from geometry class, the term locus of all points. I don't know if you remember from geometry class, like a circle is the locus of all points, equidistant from the center. Or an ellipse is the locus of all points, where the sum of the major radii and small, blah, blah, blah. Anyway, a rainbow is the locus of all points. In other words, just the accumulation or the sum or whatever of all points equidistant from your eye that makes up that nice 42-degree angle. So if I'm standing right here, there is one circle in space I can draw that meets this criteria of the sun bouncing 42 degrees from me. So the sun is bouncing off all the raindrops, but it's only a circle of them that make up this, what I can perceive as a rainbow. Let's see, I wanted to show one other, yeah, I think that's it. Let's do a quick demo of refraction and total internal reflection, and then we will talk about one more effect. Yes? No, yeah, the question is, do I need to know about anti-solar point? Now, I just Googled how rainbows are made, and I found this picture. It's the 42 degrees is the angle between the sun, the raindrop, and my eyeball. That's it. You forget about that. Don't worry about the bottom 42 degree. Yeah. Okay, let's do this. There it is. Okay. So I'm going to send some light through two different media, and the way I'm going to do that is with I've got a light bulb in here. It's one of those old-fashioned light bulbs that just gets crazy hot. So it's actually emitting a pretty good spectrum of colors, the whole rainbow. And I'm sending them into a medium. Now, what you're seeing, let's see, the red is actually, we won't talk about that right now. But what you're seeing is the light is actually slowing down in this little region right here, but you can't tell it's slowing down. But if I have the light hit the boundary at an angle, you can see it clearly bending. And so it's kind of going straight, and then when it gets to that boundary, it's slower in that medium, it's slower in the plastic, and it's going to bend toward the normal. The normal is the angle between the two mediums, between air and the plastic. Also, another thing to note, I'm hoping you can see this, all of these effects we're describing, and this kind of goes with pretty much everything we're going to talk about this half of the semester. All these effects we're talking about, pretty much all the stuff we're going to talk about, electrons and electric fields and photons, it's all probabilistic, meaning the first half of the semester when we were talking about Newton and trains and cars and falling objects and baseballs and stuff, that is sort of a Newtonian deterministic world. Turns out nowadays physics understands the world not as deterministic. So I forget if you're a Calvinist, I think he was predestination. So it turns out the world, according to physics, is not predetermined. You can't set, if I told you all of the preconditions, if I told you all of the where we were right now, I can't roll the tape forward and tell you what's going to happen later. The world is very probabilistic. And the only reason I bring that up now, well, it's just good. It's good metaphysics to keep in your mind. The world is probabilistic. It's cloudy and chaotic. But here's another reason. So I think that the light is going to bounce off that. The light is going to refract in that medium. That's actually a percentage of the light. Some percentage of the light is actually always going to reflect, and hopefully you can see the faint reflection kind of shooting off up into the left. So you're seeing both there. You're seeing most of the light refracting, but some of it is reflecting. Okay. I can do the same thing with this triangle here. But what I want you to see with the triangle is I can get total internal reflection. So what you're seeing right now is light going from a clear medium, air, into another clear medium, plastic. So there's no mirror. It should travel straight through, and it will if I hit it at the right angle. But if I hit it beyond some critical angle, I'm going to get total internal reflection, which means even though I'm going from clear to clear, transparent to transparent, beyond some angle, the light will bounce straight back. That's important for a couple phenomena that are worth knowing about. One is rainbows. So if the sun's behind me, the only way I'm getting the light hitting me in the eye is I'm getting total internal reflection inside those raindrops. So we're getting total internal reflection inside a raindrop. It's also how fiber optics works. I can send a data signal from here to the other side of the Atlantic Ocean on a cable. And the way I do that is I bounce light through a cable, through a clear cable. So it's transparent so light can go through it. But as light just kind of does this, bounces all the way down the line. And it's bounce, bounce, bounce. It goes on total internal reflection. In fact, if you want to attenuate or weaken the signal, you just bend the light you bend the tube or the cable enough, and some of the light will escape because it misses the total internal reflection, misses the critical angle. Anyway, okay. I think that's all I wanted us to see right now with these guys. So you're seeing refraction in there, but also you're seeing some total internal reflection from if I go past the critical angle. So not much light is ending up over here. Most of it is coming out over here. Question? Is it at a certain angle? Yeah, or no, it bends toward or away from the normal? Yes. Good question. The question is, these angles that we've been seeing, is it random or is it it's actually very specific based on the two speeds in the two media. And so I can measure the speed of light in plastic. And again, it's always the speed of light, but you know, in bulk it slows down. And if I measure the speed of light in air and measure the speed of light in plastic, those two, it's actually the ratio of those two will tell me the angle. So it's actually a very specific angle. So I can calculate pretty precisely the angle that when I go from air into diamond, air into water, air into plastic, plastic into diamond, whatever, I can calculate those angles using just the speeds, which is experimentally findable. Yeah, Caitlin. Good question. Now, you are seeing it's a little bit. So why is it not becoming a rainbow? It is a little bit, and well, because I've got really pretty narrow beams, and so it's slightly widening and slightly widening. And if I were to put my hand, if I were to put something better reflector over here, I'm probably going to get and actually this camera is just, a good reason is the camera is doing a bad job showing it to you. But I'm slowly getting a little bit of a rainbow as it slowly disperses. I could probably just do that, and you'll see some rainbow coming out. But again, it's pretty. You can maybe see a little rainbow on the left of one of the top column of light, but the amount of rainbow that you're seeing is. Can you kind of see that a little bit? It's kind of dispersing. Yeah. That one's pretty good. That's about as good as you can get. And then the further away, if I could shoot this like across the room, the further away, the better rainbow I'll get. So actually, I just saw it a second ago. I was getting it. I was getting onto that wall a second ago. Anyway, I can make it totally dark in here. We can play with this. But yeah, good question. Ooh, that's a good one. Pink Floyd right there. Okay. All right. Let's look at one other example of this happening. Yeah, let's look at one other example of this happening. And, oops, it's this phenomena. And again, this is your brain being really bad at telling you what's going on. So we know what that is. That's a mirage, right? Hopefully at some point in our life we've been driving a road trip across Texas or something and seen that. And your brain is so convinced that the road is wet in that picture. It's almost impossible to convince your brain, no, it's not wet. Here's what's going on. You're actually getting a very similar effect. You're getting refracted light. So let's take a look at what I'm seeing. Right now, there's a white car on the road ahead of me. If I see white car or a picture or an image of a white car coming at me from below the white car, my brain goes, oh, there's a reflective surface. I bet the road is wet. And so your brain is making up the reflection, and your brain is making up that it's wet. Neither of those are true. What's going on is light is hitting you from an angle below where the source of which must be below the road. And so your brain comes to a conclusion that the road is wet, and I'm seeing a reflection. That's actually not what's going on. What's going on is light is bouncing in a straight line to me from the car, and that's how I see the car. But light is also, I mean, you could see that car from anywhere. That means the light's going everywhere. So I could see the car from the left of the car, above the car, right of the car. So that means the car is bouncing light everywhere. And no matter where you stand, you'll see white car. And so the car is also bouncing light downward, but that light is actually being bent, it's being curved up to me. And the reason it's being curved is because I have a temperature gradient above the road. A temperature gradient, meaning sunlight all day has been shining on that nice black asphalt, and that black asphalt is crazy hot. You could cook an egg on it. So the black asphalt is crazy hot, and the air right above it is also crazy hot. But in this picture, maybe it's 80 degrees outside. So the air pretty high up is 80 degrees. The air down near the road is maybe 150 degrees. That's a temperature gradient, 80 to 150. Air bends light as it Well, light will bend as it goes from one medium to another. Hot air counts as a different medium than cold air. So the index of refraction is different in hot air and cold air. And so what's happening is light is leaving that white Maxima, I think, leaving that white car headed toward the asphalt. It was about to just hit the asphalt, be absorbed, gone forever. But as it went from cold air to warmer air to warmer air to warmer air, it kept bending, 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 and then it hit me in the eye, and it hit me in the eye at an angle that my brain interpreted as coming from down there. So here's another picture of that. Here's a picture. So the guy in the green car is getting hit by photons kind of coming up at an angle. Up above, you can see what he's thinking. He's thinking, oh, I must have gotten hit by a straight line photon, because photons don't bend. The guy in the green car is mistaken. It bent, and he's making up what's going on. He's making up that, I mean, I guess your brain could make two conclusions. Your brain could either conclude there is a smudgy white car underneath the road, or the road is wet. Both of those are wrong. The correct answer is the car's light is just traveling to me in two paths, one straight and one bent. Now, what I don't have a picture of that happens sometimes, I don't know if I've ever seen this personally, but notice in this picture, the temperature gradient goes from cold to hot. You can get a flip of that. You can get a temperature gradient where, this usually happens in the ocean, where the ocean's very cold and it's a really hot day, but the ocean, it got cold at night, so the ocean surface is cold. And so the temperature gradient goes from hot air above to cold air down by the water. And you can actually get light bending this way. And I think back in the day, you would see floating pirate, you'd be sailing and across the ocean or something, and you'd see a pirate ship in the sky. So because in this case, your brain sees a white car below the road surface. If it's bending the other way, you would see a car in the sky, which isn't going to happen on a road. Unless the road were crazy cold, I guess that wouldn't happen very often. But in the ocean, it can happen where you see a boat in the sky and people get totally freaked out that there's a flying pirate ship or something. Okay. 14 minutes, 12 minutes left. Let's talk about a couple other phenomena. Let's see, where's my list of stuff to talk about today? Talk about refraction is just bending, reflection is just bouncing. Absorption, I wrote refraction twice. Absorption just means absorbed. I don't think I have to explain that. Right now I'm absorbing not much because I'm wearing white. So my shirt is made up of chemicals that are designed to reflect most white light, but my tie is absorbing most light. So most of the light in this room is in the visible part of the spectrum. My tie is absorbing most of it. My shirt's reflecting most of it. And it's scattered. My shirt's scattering it, by the way, so it's reflecting it, but I don't look like a mirror. You can't see yourself in my shirt. I'm reflecting most light, but in a really scattered way, so I don't, a mirror also reflects light, but in a nice organized way, so you can see, it recreates an image, whereas my shirt's just all over the place. Yeah. Yeah. Wow, good question. The question about eye color and skin color. Yeah, let's see. Do we all have? Well, I could say we all have the same skin color in that color's made up. It's human perception. So we all have no skin color. But all of us have different. What is it? Melatonin that absorbs. What is it? Melanin. What's melatonin? Oh, that helps you sleep. Yeah, that too. I don't know. We all have different amounts of melanin. Yeah, we all have different. My studies are very narrow. We all have different amounts of melanin, which I think causes us to absorb or reflect different amounts of light. And so, my skin reflects most light, especially some red, holds on a little bit of blue. Other skin absorbs more. Eye color, same way. So if my eye eye color is slightly different, and something we really haven't talked about today. I do want to get to. We have to get to these two things. If we have time, we're going to talk a little bit about scattering. Eye color actually comes from a couple things. One, just reflecting. So if I have blue eyes, I'm reflecting blue. But I'm also scattering light based on literally the size of the molecules in my eye. And if you've ever looked at a glass of milk and it looks kind of bluish, similar, maybe, that similar thing is going on, that this literally the size of the molecules can cause different wavelengths to be reflected. I saw this really cool documentary. There's no way I'll be able to find it again. I was on YouTube about how they made stained glass way back in the day, and it's crazy. They figured out certain stuff to put in glass that wasn't the color they wanted to make. So they wanted to make red. They just put stuff in there. It looked like if you had a jar of it, it would look, green, like totally not red. But once it was in glass, it had just the right size of particle, and it reflected red light. I don't know. So anyway, that's eye color comes from a couple of different places. Question? All those pictures of the car was all refraction. Yeah. I am going to, I'm going to turn all the lights off real quick so we can see this one. I want to do two more things real quick before we run out of time. I have up here, I think you can see it, this yellow jar. This is soap. So I have a jar of soap, and over here that you can't see, I have a little ring like you would make soap bubbles with. And then a picture of that ring is about to be projected over there. You can kind of see the ring. There's my hand. My hand's being, whatever here is being reflected over that wall. And so I'm going to make some soap bubbles by putting soap onto that ring. And so there's my soap bubble. It should look familiar. And so what you're seeing is light being reflected. Pretty much all light. It's white, right? But if we wait long enough, gravity's actually going to pull the soap down, and I'm going to start seeing some colors. And hopefully this is familiar. Hopefully you've seen like an oil slick on the highway, or we've seen colors in soap bubbles. You're seeing the same thing here. One thing to note, this image is upside down. So that's the bottom, and this is the top. But that's not totally, well, it becomes important in a second. So here's what you're seeing. You're seeing the thickness of the soap bubble is actually about the thickness of a wavelength of light. So I mentioned that red light is about 700 nanometers, blue light's around 400 nanometers. You can make very thin films, and sometimes this is called thin film interference. You can make very thin films, and here's what's going on. Light is bouncing off the front surface of the bubble back to the screen, and some light, again, it's probabilistic, some of the light's actually going through the front and bouncing off the back. So what I'm getting is I'm getting light bouncing off two places and shooting back at the screen. Some's reflecting off the front surface of the bubble, some's going off the back surface of the bubble. And light being a wave, it's interfering with itself. And so if the red light, if the bubble's kind of thick, I will destructively interfere. I'll get red light destructively interfering. In other words, the longer wavelengths. So if the bubble's kind of thick, I'll get red light canceling itself out. And so I'll be left with blue and green, and I'll get a nice teal. If a middle wavelength is canceling out, I'll get that. And if just the blue gets canceled out, I'll get yellow. And so what I want us to see is, first of all, those cool colors, but I can even understand a little more what's going on. First of all, did you see how there were stripes? Because what was happening is where it's thinnest, I was getting one wavelength of light canceling out because it was thick as one wavelength of light. Just below it, the soap bubble was thick enough that it was 2 wavelengths thick. And I could still cancel out because it was 2 wavelengths thick. And then it's 3 wavelengths thick. And so you can see that the colors go through a cycle. The colors go through a cycle of 1 wavelength of red, Roy G. Biv, then 2 wavelengths of Roy G. Biv, and 3 wavelengths of Roy G. Biv. And then at the top, which down here is the bottom, the last thing I should see is yellow. Yellow is when blue, which is the shortest, is canceling out. So as the soap film falls due to gravity, and probably me waving my hands is screwing up the air currents, screwing it up. But I'll stand over here. But what you should eventually see is yellow should be the last thing you see before it pops. Because yellow is when it's really, really thin. It's really, really thin, and the shortest wavelength, blue, is canceled out, and we're left with red and green, and we see yellow. Maybe that's going to happen. Come on, gravity. And then actually, what you might see right before it pops is yellow with black on top, or because it's flipped, black on the bottom. Black because all the wavelengths are canceling out. You're getting complete destructive interference. So a pretty cool example of destructive interference. You get the bands of color as you go through Roy G. Biv, kind of integer sets of wavelengths. And then at the very bottom, which is the top in reality, you get yellow then black. And it's just hanging in there at this point. Okay. 4 minutes left. We're going to talk about fluorescence, and then we're done. Come on, yellow. It is so slow. Actually, maybe this is a good time to turn on my black light. Yes. Okay, the question was about the wavelengths canceling out. They're literally, let's see if I have a picture. Well, that's not a great picture. I mean, I'll just say this. Oh, did I miss it? That's fine. Okay, 3 minutes left. Because it's a wave, if I get a red wave crest traveling with a red wave trough, they will completely cancel each other out. I will get two sources of light. So the front of the bubble and the back of the bubble are two sources of reflection. And if it's just the right thickness, I can get a red wave and a red wave totally canceling each other out. It's called destructive interference. I think we have enough time to talk about fluorescence. And the only thing I wanted to talk about, really say about fluorescence was, as we're talking about the spectrum, I think most of us are familiar with black lights. Black lights are just lights that are emitting mostly light out of the visible part of the spectrum. And so the most useful lights for humans are lights that emit visible light, like Roy G. Biv. Some lights are for parties, and they don't emit Roy G. Biv. They emit just past Roy G. Biv. They emit black light, which is a weird term. It's really just ultraviolet. It's beyond violet, ultraviolet. And there are certain chemicals we've come up with, the Tide box itself and the Tide detergent. There are certain chemicals we've come up with that shift their absorbed light over a little bit to the left. And so what Tide does to make your shirt look white is it absorbs light that you wouldn't normally see, and it shifts it over, and you get this nice blue-white. You don't want your clothes to look dingy yellow, so you want to replace any blue that you're missing, or even just make up blue, and that's kind of what it's doing. It's kind of making up blue. It's absorbing ultraviolet, shifting it slightly lower in energy, and giving you nice blue colors. And I don't know if you can see all that stuff up there from the way back, but anyway, I just have a nice selection of, I think the Tide box is probably the best one. I have a selection of things that do that. Markers and crayons and stickers and highlighters just do that. They absorb light that's maybe not visible to you, and they shift it over a little bit and emit stuff in the visible part of the spectrum. I totally forgot to do an eye click. Wait, it's 45. I have 1 minute. We're going to practice. Just one eye clicker real fast. Quick, just buzz A and you can go. We're practicing deciding how, we're practicing our understanding of additive colors. Pardon? Oh, seriously? Then we might be, wait, nope, wait. Okay, sorry about that. It's plugged in now. It wasn't plugged in. So I've got my magenta shirt, my nice outfit. I'm going to illuminate with just green. So the shirt has no green in it. It's going to look black. But the tie, which is reflects green, will look green. So black, green. There you go. Have a nice day. See you Friday.